I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss a very important numericals on waves and waves in one dimension. Now before going to do the numericals, we will try to list down the formulae that we are going to use in the numericals. So the first one is related to the velocity of a transverse wave. So the velocity of a transverse wave is given by V is equal to under root T by mu, where V represents the velocity, T is the tension in the string, and mu represents the mass per unit length. This is mass per unit length. So given T and mu, we can very easily calculate the velocity of a given transverse wave. Now the next formula is Sg, that is the specific gravity is given by mu upon area. If you are given mu and area, you can calculate the specific gravity, or in some numericals, we need mu to calculate the velocity. And if mu is not given, only the specific gravity and area are given, then we can use this formula. So Sg here represents the specific gravity. It is the specific gravity which is denoted by S suffix g. And mu we have already seen, it is the mass per unit length. In some cases, if mu, the mass per unit length, is not directly given, we can use the formula capital M by L, that is total mass divided by total length. That gives us the mass per unit length. And area A represents the area. So if the area is given, we can directly use it. Or for a string of uniform cross section and circular in diameter, we will use the formula pi r square. Now coming to the longitudinal wave. So what is the formula for calculating the velocity of a longitudinal wave? So V is given by under root Y by rho. So V here represents the velocity. The velocity of the wave, that is the longitudinal wave we are talking about. Y represents the Young's modulus. Young's modulus is always related to the linear expansion of the wire. So Y denotes the Young's modulus and rho denotes the density. So we have V is equal to Y by rho. In some cases, if V and rho are given and we have to find Y, we will simply do the squaring on both sides. V is equal to under root Y by rho. We can directly use the formula, or we can do squaring on both sides, and from here we can write the formula. We will transpose rho onto the other side. So we have Y is equal to V square rho. Now we also have this basic or the fundamental formula for the velocity of a wave, which is given by V is equal to F lambda. F here denotes the frequency. So when we are talking about velocity, velocity always depends upon the frequency and wavelength of the wave. So lambda here denotes the wavelength. Sometimes we also use n for frequency. We can use n also, then we write V is equal to n lambda. In some cases where n is already used in the expression, we may use nu. Nu also denotes the frequency. So these are different notations we use for frequency. Here we are denoting it by F. Now coming to the frequency of a stretched string, which we have already discussed in the laws of stretched string. So the frequency F is given by 1 by 2L under root T by mu. So here L denotes the length of the string. L is the length of the string. T is the tension in the string. And mu is the linear density we call, or mass per unit length. Both mean the same. Linear density or mass per unit length. And F here, as we have seen, denotes the frequency. Now if we have to get mu, that is the mass per unit length, it is given by density into area. We all know the formula for density. Density is equal to mass per unit volume. Mass upon volume. So I will just try to rearrange this formula and write. I can write density is equal to mass upon, for volume, I will write length into area. We have L into B into H. So if the cross section I take, B into H is giving us the area multiplied by the length. So M by L, that is the mass upon total length, gives us the linear density mu. So we are going to write it as density is equal to mu upon area. So this implies mu is equal to density into area. So if you are very thorough with the basic definitions, you can deduce any expression you want. So here mu is equal to density into area. Density is usually represented by rho, and the area of cross section, because it is circular in cross section, we are using pi r square. So mu is equal to rho into pi r square. So we are going to use all these formulae while doing the numerical. So this we have already seen. Mu is capital M by L, mass per unit length, which is the linear density. Now let us start with the numerical. A sonometer wire of length 0.5 meter is stretched by a weight of 5 kilogram. The fundamental frequency of vibration is 100 Hertz. Calculate the linear density. So first let us write the data given. What is the data given? So the length of the wire is given, L is equal to 0.5 meter. It is stretched by a weight of 5 kg. Here weight or the mass is given, that is 5 kilogram. And the fundamental frequency of vibration, N, is equal to 100 Hertz. We have to calculate mu. So which formula we are going to use? We are going to use the laws of stretched string. The formula N is equal to 1 by 2L under root T by mu. So N is given, L is given, T is not given, but mass is given. So we can calculate tension using the formula T is equal to mg. Here it is mentioned as weight. If it is weight, it should have been given as mg Newton. So we consider it as mass in kilogram. So T is equal to the tension in the string is given by mass multiplied by acceleration due to gravity. So the value of G, acceleration due to gravity, we take it as 9.8 meter per second square, because all the other quantities are in the SI system. So we are going to take the value of G also in SI. So tension T is given by M. What is the mass? 5 kg multiplied by 9.8. So we got T, we have to find mu. So let us now write the formula for mu. So I can write 2NL is equal to under root T by mu, or 4N square L square is equal to T by mu, So this implies mu is equal to T upon 4n square L square. So we are going to use the formula mu is equal to T upon 4n square L square. This is the formula we are going to use. This is coming from our fundamental formula for frequency. N is equal to 1 by 2L under root T by mu. So let us now do the substitution. Mi is equal to, what is the value of T we got? 5 into 9.8 upon 4 into n square. N is the frequency. Frequency is 100. So 100 into 100 square. No? Into L square. L square is 0.5 into 0.5, or you can write it as 0.5 square. Now for simplification, you can use your calculator and you will get the value as 4.9 into 10 power minus 3 kilogram per meter. So this is the value of mu. The linear density is nothing but the mass per unit length. So we are writing the unit kilogram per meter. So the answer here is 4.9 into 10 power minus 3 kilogram per meter. Now coming to the second one. A wire whose linear density is 5 into 10 power minus 3 kilogram per meter is stretched between 2 points with a tension of 450 Newton. The wire resonates at a frequency of 420 Hertz, and the next higher frequency at which the same wire resonates is 490 Hertz. What is the length of the wire? So first what we have to write is write the data given. Here the linear density is given directly. So mu is equal to 5 into 10 power minus 3 kilogram per meter. And this wire is stretched between 2 points of tension 450 Newton. The wire resonates with a frequency. I write N1 is equal to 420 Hertz. And the second one is N2 is equal to 490 Hertz. So first what we need to do is we need to calculate what is the harmonic here. So N1 is to N2 is 420 is to 490. So 0, 0 will get cancelled. So we get 6 is to 7. This is the ratio we are getting. This is the first harmonic if you imagine. So this will be the next harmonic. So how we are going to write the formula for frequency now? N is equal to 6 by 12 under root T by mu. So this is the formula we are going to use because this is the first harmonic we are seeing at 6. So 6 by 12 under root T by mu. Now we have to calculate the length of the wire. L is equal to how much? So let us modify. L is equal to 6 upon 2n under root T by mu. So in this we can directly do the substitution. So L is equal to 6 upon 2 into what is our N? 420. First frequency we are taking. So upon 420 under root T. What is the tension? 450 upon mu. Mu is 5 into 10 power minus 3. So we can simplify it. L is equal to 6 upon 840 under root 450 by 5 will give us 90 into 10 power 3 if I take that to the numerator. So L will be equal to 6 upon 840 into, this is under root 9 into 10 power 4. So 9 under root 9 will give us 3 into 10 power 4 under root will give us 10 power 2. So when you simplify, you get the value as 2.1 meter. So the length of the wire here is 2.1 meter. So the length of the wire at which the wire resonates is 2.1 meter. Now the next one. In order to double the frequency of the fundamental note emitted by a stretched string, the length is reduced to 3/4 of the original length. The length is reduced to 3/4 of the original length. By how much the tension is to be changed? So, first thing we have to take is the frequency has to be doubled and then the length has to be reduced to 3/4. So, what is the change in tension? So, let us put it as the data. In order to double the frequency, so our N2 should be equal to 2N1, that is double. And the length is reduced to 3/4 of the original length. So if I take the new length as L2, the original length as L1, so it will be 3/4 L1. So by how much the tension is changed means T2 is changing by how much? That is what we have to find. Now write the formula. N is equal to 1 by 2L under root T by mu. So here only the frequency is changed and the length is changed. But the mass per unit length remains the same. The total length of the wire may change, but mass per unit length always remains the same. So how we are going to write the formula? N1 is equal to 1 by 2L1 under root T1 by mu. And N2 is equal to 1 by 2L2 under root T2 by mu. So we want to find the tension. So let us try to write the formula for tension. So from the first formula, T1 is equal to, if I am squaring on both sides, 4 N1 square L1 square into mu. I take 2L1 here, 2N1 L1. So if we are squaring, 4 N1 square L1 square into mu will give us T1. So what is T2? Will be 4 N2 square L2 square into mu. Since we have to find T2, we will take the ratio of these two. T2 by T1 will be equal to 4 N2 square L2 square into mu upon 4 N1 square L1 square into mu. 4 and 4 will get cancelled. Mu also gets cancelled in the numerator and denominator. So we want T2, so we can write it as N2 by N1 whole square into L2 by L1 whole square into T1. So what is our N2 now? 2N1. So 2N1 by N1. What is our L2? 3 by 4 L1 by L1 whole square into T1. N1 get cancelled. L1 also gets cancelled. So what we have here is 4 into 3 by 4 whole square is 9 by 16 T1. Or we can also simplify it and write it as 4. So 9 by 4 T1. So how the tension is changed? It will become, the tension will now be 9 by 4 times the initial tension. So this is our result. T2 will be equal to 9 by 4 times T1. This is how it is changing. Now, let us look at another formula. When the fundamental frequency of a wire is increased by 6 Hertz, the tension is increased by 44%. Keeping the length constant, find the change in fundamental frequency when the length of the wire is increased by 20%, keeping the tension same. So we will do it in parts. First, what we will do is we will keep the length constant and we will only find the frequency, the initial or the fundamental frequency. Then using the same fundamental frequency, we will find keeping the tension same when the length is increased. So let us write the data. The fundamental frequency of a wire is increased by 6 Hertz. So I can write N2 is equal to N1 plus 6. And the tension is increased by 44%. So T2 is equal to T1 plus 44% of T1. Means I can directly write it as 1.44 T1. Can write it as 44 by 100 as 0.44. So 1 T1 plus 0.44 T1, we get 1.44 T1. Now we are going to keep the length as a same. Length remains the same. It does not change. If you are taking it as L1, it is L1. L2 is equal to L1. So what we are going to do now is we have to find the frequency. We will first find the fundamental frequency. So how we are going to do it is N2 by N1 will be equal to, because the length remains the same, we are going to write T2 by T1 under root. Because mu also remains the same, the length remains the same, the linear density also remains the same. So we can directly use the formula N2 by N1 is equal to under root T2 by T1. So how do we get, what is N2 now? N2 is equal to N1 plus 6. N1 plus 6 upon N1 is equal to under root, what is T2? 1.44 T1 by T1. So T1 and T1 will get cancelled. N1 plus 6 by N1 is equal to under root 1.44. So this is nothing but 1.2, because square root of 1.44 is 1.2. Now let us do the cross multiplication. N1 plus 6 is equal to 1.2 N1. So I'll bring N1 onto the other side. So this implies 0.2 N1 is equal to 6, or N1 is equal to 6 upon 0.2. So we get 60 by 2, that is 30 Hertz. So 30 Hertz is our actual frequency. Now what they are telling, find the change in fundamental frequency, means the frequency is going to change when the length is increased by 20%. So now what we are going to see, the length is going to increase by 20%. So it will be L1 plus 20% of L1. It is going to increase by 20%. So L1 plus 20%. 20 by 100 is what? 0.2. So I can write this straight away as 1.2 L1. L2 is equal to 1.2 L1. Now we'll use the formula N1 L1 should be equal to N2 L2. So how do we get N2? N2 is equal to N1 L1 upon L2. So our N1 now is 30 Our L1, I'll write it as L1 upon L2 is 1.2 L1. L1 gets cancelled, and 30 upon 1.2, we get N2 as 25 Hertz. So the new frequency is 25 Hertz. They are asking us to find the change in fundamental frequency. So how do we get the change? Change is given by N1 minus N2, that is 30 minus 25, that is equal to 5 Hertz. So the change in frequency is given by 5 Hertz. Now the fifth one. Calculate the speed of transverse waves in a wire of 1 millimeter square cross section under the tension produced by 0.1 kg weight. And the specific gravity of the material is 9.81 gram per centimeter cube, and G is 9.81 meter per second square. So first let us write the data. What is the data given? The area of cross section is given as 1 millimeter square. So we are writing A as 1 millimeter square. And the tension produced is 0.1 kg weight. So what is the tension? 0.1 kg weight. And specific gravity of the material, which is denoted by Sg. S suffix G represents the specific gravity, which is 9.81 gram per centimeter cube. And then G, the acceleration due to gravity, is 9.81 meter per second square. What we have to find is the speed or the velocity is how much. So one thing you need to focus here is area is given in millimeter square. Sg, the specific gravity, is given in gram per centimeter square. And acceleration due to gravity is given in meter per second square. So there is every need to do the conversion of units. We have to convert all the quantities into the same system of units. So we'll be doing it in SI system. So we will convert this millimeter square also into meter square and the specific gravity into kilogram per meter cube. So first we'll do the conversions. Write the formula and then we'll go for conversion. So what is the formula we are going to use here? V is equal to under root T by mu. So T is given, but mu we have to find. So which formula we are going to use to find mu? Because we are given the specific gravity and the area. So we'll use the formula mu is equal to Sg into area. The specific gravity multiplied by the area. So we will get mu from here, then substitute here and get V. So before substituting, let us see the conversions. Conversion of units. So Sg is given in 9.81 gram per centimeter cube. So how do we convert grams? So 1 gram is 10 power 3 kilogram. I'll write it here. Sg is equal to 9.81 gram per centimeter cube. So first I will write the grams in kilogram. So it will be 10 power minus 3 kg. And centimeter cube, I'll write it as 10 power minus 2 meter whole cube. Because 1 centimeter is 10 power minus 2 meter whole cube. So what we are getting here, Sg is equal to 9.81 into 10 power minus 3 upon 10 power minus 6. And when this minus 6 comes up, what we have is 10 power plus 3. This will be in kilogram per meter cube. Minus 3 and plus 6 gives us plus 3. So we have 9.81 into 10 power 3 kilogram per meter cube. So that is the conversion for Sg. Now the tension here is given in kg weight. We need to convert it into Newton. So multiply it with 9.81 because tension is equal to m into g. So 0.1 into 9.81 we get 0.981. And then area in millimeter square. So we need to convert this millimeter square to meter square. So 1 millimeter is 10 power minus 3 meter. So if I have to find the square of it, so 1 millimeter square will be 10 power minus 3 meter whole square. That is why we get 10 power minus 6 meter square. So we will substitute these values in the given formula now. Mu is equal to Sg into area. So let us first find mu. What is the value of Sg we got? 9.81 into 10 power 3 after conversion. And the area we got 10 power minus 6 meters square. So let us do this. Minus 6 and plus 3 gives us 10 power minus 3. So 9.81 into 10 power minus 3 is the value of mu. Mu is equal to 9.81 into 10 power minus 3. Now substitute for V. V is equal to under root T by mu. T what we got? 0.981 Newton after multiplying it with G. And mu is 9.81 into 10 power minus 3, which we have just got the value. When we substitute, so we get 10 meter per second. You can do the simplification 0.981 upon 9.81 into 10 power minus 3. I can take it into the numerator. So we get under root 100. That is 10 meter per second. So the velocity with which the wire vibrates is 10 meter per second. Now the next one. A copper wire of radius 10 power minus 3 meter has a wavelength of 1 meter. It is fixed at both the ends and is subjected to a tension of 10 power 4 Newton. Calculate the fundamental frequency and the frequency of the first two overtones. So you need to understand what is the data given and what we have to find. Before proceeding, what I want to tell you is whatever we have discussed regarding the fundamental frequency, the harmonics and the overtones. We have already discussed about harmonics. So if you say the fundamental overtone will be the first harmonic. Fundamental is the first harmonic N1. Okay. Now the second harmonic will be N2. Then N3 and so on. Now, if I have to find the first overtone, the second frequency will be the first overtone. Third one will be the second overtone. This you need to keep in mind before we proceed further. So what is the data? So it is given that the wire is fixed at both the ends. So whenever we are fixing a wire at both the ends, this is the least mode of vibration. You will have a node at this fixed end and also a node at this fixed end. So in between the two nodes, we have an antinode. So this is a node, this is a node, and there is an antinode in between. This is the fundamental mode of vibration or the first harmonic. So because it is fixed at both the ends and we are trying to calculate the fundamental frequency and the frequencies of the first two overtones. So in the first harmonic, this is the case. Now we know that the distance between any two nodes is given by lambda by 2. Between two nodes it is lambda by 2 and that is nothing but the length of the wire now. Lambda by 2 is equal to N. So write the data given. The radius is given 10 power minus 3 meter. So R is equal to 10 power minus 3 meter. And the wavelength is 1 meter. So lambda is equal to 1 meter. And it is subjected to a tension of 10 power 4 Newton. So T is equal to 10 power 4 Newton. And also the density of copper is given. Rho denotes the density. Is 8.92 into 10 power minus 3 kilogram per meter cube. First we have to find F1. Maybe if you are talking as the fundamental as F, So the second frequency or the first overtone will be F1 and the second overtone will be F2. So the formula we are going to use is the same. F is equal to 1 by 2L under root T by mu. And mu is not given directly because the density is given and the radius is given. We can calculate using the formula density into area, that is rho into pi r square. So what is our L? L is equal to lambda by 2. I have explained it with the help of this diagram how we are writing L is equal to lambda by 2. Now first let us find mu. Mu is rho into pi r square. Rho is given directly. And pi 3.14 into r square. R is 10 power minus 3 meter. So squaring it we get 10 power minus 6. So the linear density is 28.008 into 10 power minus 9 kilogram per meter cube. So this is in the SI system. Now let us write for lambda by 2. L is equal to lambda by 2. Lambda is 1 meter. So 1 by 2, that is 0.5 meter. So we have got mu, we have got L also. So let us substitute in the formula. F is equal to 1 by 2L under root T by mu. So for L, we are going to substitute 0.5. For T, the tension, it is 10 power 4 given in the numerical. And mu, we have calculated the mu to be 28 into 10 power minus 9, approximating. We are trying to approximate and write it as 28 into 10 power minus 9. So we get 597614 Hertz. Or we can also write it as 597.614 kilohertz. Because it's the frequency is very high, we are going to express it in kilohertz. Because 1 kilohertz is equal to 10 power 3 hertz. 1 kilohertz is equal to 10 power 3 hertz. So this will be the frequency. Now what we have to find? The first overtone. First overtone F1 will be equal to 2F. So 2 into 597.614, that gives us 896.4 kilohertz. Then F2 is equal to 3F. F2 is 3F. So what we are going to write now is 3 into F. So 3 into 597.614, that gives us 1792.8 kilohertz. So these two are the first overtone and the second overtone. Now the next one. A wire 50 centimeter long and of mass 6.5 into 10 power minus 1 kilogram is stretched so that it makes 80 vibrations per second. Find the stretched force in kilogram weight. We have to find the force in kilogram weight. So let us put down the data. So the length is given 50 centimeters long. So we are writing it as L is equal to 50 centimeter. We are directly converting it and writing it in SI system 0.5 meter. And mass is 6.5 into 10 power minus 1. 6.5 into 10 power minus 1 kilogram. We can directly write it as 0.65 kg. And it makes 80 vibrations per second. That is the frequency. So F is equal to 80 per second. We have to find T, that is the stretched force or the tension. But we have to convert it in kilogram weight and represent. So we have to find the tension. Because it is given as stretched force, you cannot consider it that is the force. The stretched force gives rise to the tension in the string. So we have to calculate the tension in the string. So which formula we are going to use? F is equal to 1 by 2L under root T by mu. we will modify this formula and write. So T will be equal to 4F square L square mu. Squaring on both sides and rearranging, we get T is equal to 4F square L square mu. Because we are trying to write it in terms of known values. So how we are going to get mu first is m by L. Mass is given, total length is given. So first let us find mu. Mu is equal to capital M by L, total mass upon total length of the wire. So 0.65 upon 0.5, that is 1.3. So this is the mass per unit length. Then substitute for T. T is equal to 4F square L square mu. 4, what is our F? We got 80 per second. So this is F square. And mu, first we'll write L square. So what is our L? 0.5 meter. So 0.5 meter square multiplied by mu, which is 1.3. So when you multiply, you can use your calci to find the answer. That will be 8320 Newton. So the stretched force is 8320 Newton. But we have to express it in kilogram weight. So in order to express in kilogram weight, what we do? We'll have to divide it with G. So 8320 divided by 9, because I have given the formula T is equal to mg. So if we have got the tension, we know the mass, or we have to find the mass. So m will be equal to T upon G. So the tension here we got it as 8320 newtons divided by the value of G, acceleration due to gravity, as 9.8. So we get 848 kilogram weight. So it is 848 kilogram, or we call it as kilogram weight. Now one more problem we'll do. A metal rod 150 centimeter long is fixed at the center. When it vibrates longitudinally, the frequency is found to be 1200. Calculate the Young's modulus of the material of the rod, and its density is 8 gram per centimeter cube. See here, the length is given in CGS. The density is also given in CGS, and frequency is 1200. That will be vibrations per second. So the unit remains the same in any system. So we can continue doing this numerical in CGS system. So first let us understand what is given. We are taking a metal rod which is fixed at the center. So you can see here the figure. Now the metal rod, this is the metal rod which is fixed here at the center. Now this is vibrating longitudinally. So when the particles vibrate longitudinally, you will have waves like this. So how will it vibrate? Always at the fixed end there will be a node. So this is the node here at the fixed end, and these two ends are open. So you will have an antinode here. This is an antinode, and this is also an antinode. This is the node. Now we have seen in our basic definition, the distance between a node and an antinode is given by lambda by 4. This is again lambda by 4. Or you can directly write the distance between any two antinodes is lambda by 2. So the length of the wire is now denoted by lambda by 2. So with this understanding, we'll go to do the numerical. So what is the data given? L is given as 150 centimeter. Rho is given as 8 grams per centimeter cube. And the frequency is 1200. We have to find Y. So what is the formula for Y now? V is equal to under root Y by rho. So Y is equal to V square rho. So first we will substitute for L. L is equal to lambda by 2. So we understood why L is equal to lambda by 2. Or lambda will be equal to 2L. If I have L is equal to lambda by 2, so lambda will be equal to 2L. And the formula for V is F lambda. So here I can write for Y is equal to V square rho, we can write F square lambda square rho. V square rho can be written as F square lambda because we are substituting for V, F lambda. So what is the value of F we have? 1200. So this is 1200 square. Lambda is given as 2L. L is 150. L is equal to 150 and lambda is equal to 2L. So this will be 300 centimeter. So 300 square into density, rho is 8. So when you multiply, you can get the answer using calci. 10.36 into 10 power 11 dyne per centimeter square. So we are taking all the quantities in CGS system. So we are going to write this Young's modulus also in CGS. So it is dyne per centimeter square. The value is 10.36 into 10 power 11. So with this, we will stop our discussion on numericals and see you again in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.